Good evening, everyone. Thank you, Peter. Thank you, Ted, for inviting me here tonight to talk to you. You've been working all day on very pragmatic, hands-on things related to building energy efficiency. I work for a company that has people who do building energy efficiency, and I'm not that guy. So I'm going to be trying to appeal to your alter ego, if you will, tonight. I'm going to talk about what's kind of going on in the power grid, power generation, and in particular the need for energy storage and some of the technologies that people are working on. Some of these are concepts. Some of them are rather fanciful. Some are established. And it's really just kind of give you a little technology tour. This is informal. Ask me a question at any point in time. It's not a comprehensive set of technologies, so they're not endorsements. They're not the ones I think are the most promising. But I'm a consultant, so unlike you guys who are out there helping students turn wrenches, I'm just usually doing paper processing and making phone calls. And where most of this material comes from is I work for Electric Power Research Institute. That's one of my main clients. It's kind of like a national lab for the power companies. And I have a job where I call up the developers of these different energy storage technologies and interview them and write up some synopses. So that's mostly where I've come by this information. The other thing that we do is take people on tours of power plants. The other thing I'll talk a little bit about is power plants that balance the load from all the intermittent wind and solar coming on the grid. This is a big issue for utilities all over the world, and there's certain spots where that issue is hitting a little bit sooner. California is one of those. And so that's let me just kind of walk you through a tour here. I'm going to try to keep on time, so I might zip through a couple slides pretty quick, but go ahead and ask any questions. And then I guess by way of disclosure, I will say I'm a mechanical engineer, and I was a college roommate of your colleague, Ted Walensky.
Sorry. And his name is Rich Myhre, and he's with Frontier Energy.
Yeah, oh yeah, there we go. Here,
Vice President.
There we go. So these are the main three areas that Frontier Energy works with. I'm basically this guy. So I work with power plants. I'm not going to talk about it tonight, but I'm happy to answer any questions about hydrogen fuel cell vehicles, which is basically, we've got them here in California. You've got gas stations that have a separate island where you can pump up with compressed hydrogen. And so we're kind of the competitor to Tesla, if you will. So it's a faster fill than electric charge, longer range than electric charge. You can't fill your tank at home. But that's for another presentation. Frontier Energy is a relatively new company made up of now six independent consulting companies. And what we have in common, we all have a common parent, the Gas Technology Institute of Des Plaines. You may have heard of that. And so the different offices here have certain specialties. Casanova, they specialize in combined heat and power. They do a lot of monitoring of actual performance. They have a contract with NYSERDA. NYSERDA did something I think is pretty interesting, which is they have an incentive program. They say, look, we'll help you, we'll give you some incentive money towards a combined heat and power install. This is mostly on large commercial industrial customer sites. And in exchange for that incentive, you have to make data available for a minimum of 3 years. They put it out on a website so that designers of future systems will have real-world data to draw upon. The office here in San Ramon specializes in commercial food service equipment. Maybe some of your labs get into that. West Sacramento, they're the vehicle folks. Oakland here is a little bit of everything. Davis is the building energy efficiency office. And Austin does a lot of, Chanhassen, this is the newest addition. They do a lot of energy audits, commercial industrial. So anyway, enough about the company. Let's talk about what's going on in the grid. This is probably not news to you, but we're seeing an influx, large influx. Basically, all the money is going into wind, solar, and natural gas. That's what new power plants are usually one of those three. So we're getting less coal. We're getting less need. Load growth is slowing. There's retirements. There's intermittent power. And so we need more load balancing plants for the renewables, fewer base load plants, and grid support services is growing. So basically, power companies in competitive power pools are making less money these days on the megawatt hours and more, except for certain times in which they make a lot of money for their megawatt hours. And they're making more money on balancing reserve, frequency control, reserves, and other sorts of fast response grid services. As you know, we're seeing more smaller distributed generation, microgrids, and this is all causing growth for energy storage. The other thing I work on is carbon capture and storage, carbon sequestration. Not going to talk about that tonight, but if you got any questions about that, feel free to ask that too. So this is the California Independent System Operator. This is the duck curve. This first came out in maybe about 2013. It got to be pretty famous pretty quickly because of its shape. But essentially, what's turned upside down is used to be peak load was mid-afternoon in the summer, hot summer day, because of all the air conditioning and other daytime business loads. And now with all this solar coming on the system, they actually have situations where the 2 p.m. price of power on a sunny day, cool sunny day. You notice here they put March 31st, not July 31st. But on a day that there's not too much AC load, there's so much solar on the system that you're having to throttle back on all the other plants that you can dispatch. And then as the evening comes and the sun goes down, it's full speed ahead, as much power as you can for this steep ramp up. California peak is now in the early evening rather than the middle of the afternoon. And so the ISO is worried about over-generation, right? There's been, I'll show a little slide, an outdated slide in a minute on renewable portfolio standards, right? The politicians have had this I'll see you and I'll raise you strategy on who can be greener and raise the renewable portfolio standards. Well, we're getting to the point that they're having to curtail renewables because there's too much renewables. You've got you can't modulate a nuclear plant. Fossil plants that were originally built for base load or load following are now going through wild oscillations in their load. And so the grid is changing. So that's what's going on. So here, California, this was the projection made in this earlier in the decade. And already by 2017, they had hit the load point had dropped down there to 2020. So the ducks arrived early. And this is just continuing. This is a slide I borrowed from a utility in the Southwest here. It's a relatively small utility. But what else is happening? Besides this shift in load, the wind turbines, it's basically a variable speed drive generator. And solar, you got clouds, you got other things. And so what was the oscillation in demand, this is what the grid sees and is trying to balance. This was their actual for 2016. This is their projection for 2024, just because of all the renewables coming on the system. So you're dealing with shifting loads, and you're dealing with a lot of basically intermittency and the issues you have to solve, right? Trying to keep your sine wave nice and smooth and your frequency right is a growing challenge. Okay, I mentioned this renewable portfolio standard. This is an outdated slide. It's basically everywhere. So these are essentially requiring utilities, more or less, whatever it costs, you have to buy it. Now, the price of wind and solar has been coming down. You will hear people say, it's cheaper than coal and all this other stuff. Well, that's true on a unit of capacity basis. But it's not really, you're going to get maybe 35% capacity factor out of a wind turbine, 20-something out of a photovoltaic panel. You got a plant that burns a fossil fuel, you can run that thing around the clock when you want. So there are people out there citing statistics that you just need to factor in, put them in context. What are the utilities doing in response? Gas turbines and recip engines. This has been a growing thing. So my cocktail party conversation to people was the grid's kept in balance by the guy on the throttle of a jet engine hooked up to a generator, which was generally true. Now, in some cases, you're having to do so much back and forth, right? A gas turbine, pretty good load, efficiency down to about half load. Minimum load it'll run is like 30% load. They have literally, in the gas turbine world, power plants the combined cycle power plants use very large, they call them heavy frame turbines. But these, it's kind of an adaptation from the peakers, as they are called aeroderivatives. They literally are derived from jet engines. And so they have good efficiency, they fast start, they ramp, they do all these things. But sometimes full throttle isn't enough throw. So you build a hall with 10 to 12, 3 or 4 up to 10 or 12 engines. This engine right here, it's not to scale, but this has got 18 cylinders. It's about 1 megawatt per engine. They burn gas. These are originally adapted from marine diesel. Well, now they fast start. You can start them up in 5 minutes. They have good part load efficiency. They burn gas, so they're clean. They have, catalytic reduction controls on the back end. And you're seeing these put in for balancing the wind and solar. And in some cases, you're seeing them put in to replace other baseload capacity, retired coal plant. We took a tour. We take groups to go visit these plants. They're fairly new. This summer, went to Marquette, Michigan, up on Lake Superior. One coal plant retired. They put in 2 of these engine plants. So now that's their primary source of generation there. And everybody in town I talked to, they knew the coal plant retired. They knew it was natural gas that was replacing it, but they didn't know it was an engine as opposed to a gas turbine or a gas boiler or anything else. All right. So that's something that's kind of a newer trend. They also are making even combined cycles now that can start faster, ramp more. I mean, this is a big deal in the gas turbine world, this flexible operation. Then, the other thing that's going on, when you think of energy storage, people think about, there's lithium-ion batteries. And there are a growing number of lithium-ion batteries. I'm mostly going to talk about all the other stuff that's not lithium-ion batteries tonight. But you can put in a small amount of batteries with one of these. In this case, I borrowed the site. Wärtsilä is an engine company from Finland. So they're offering this package. They'll have the integrated, one connection to the grid that has the battery plant on site with their engine plant. Capacity of the battery plant is small compared to the engine plant. But the engine plant, you can start it up in 5 minutes. You keep it warm, so it's not in cold. It's you keep basically the jacket water circulating, and that keeps the lube oil warm. They have it on a slow turn, so when you get the signal from dispatch, they can fire that thing up pretty quick. But now what they're doing is they're saying, look, we'll put in a battery plant. Let's say the engine plant is, 110 megawatts. 112, there it is, okay. put in a 20 megawatt battery plant. It doesn't have to run very long, but that way, instead of 5-minute response, you got a 1-second response. So you fire up the battery. So what can happen in some cases when the grid needs some help, the incidents are short. So less than 15 minutes. So it may be that you're getting paid to have the capability for that instantaneous response with your battery, and you get the signal. The problem may be solved before you even have to bring your engine fully on. So you can actually, potentially, of course, they sell this, but their claim is you'll actually run your engine for fewer hours, but you'll make more money because you got the battery paired with it. We'll see. So, but that's the hybrid plant. So I was asked to talk about hybrid plants. The other thing that's going in is at existing peaking plants. They're going in and putting in these batteries also at those peaking plants because they tend to be closer in to load centers, whereas your central stations were farther away. Go ahead.
I was just curious, on these short duration outages, this sounds like it would be a good application for the flywheel technology.
I'll talk about flywheels here in a minute too. Yeah, flywheels are out there too, and you're solving perturbations on the grid. Yeah, as opposed to a tripped unit necessarily. But yes, I'll cover some of that. Okay. So in the energy storage world, there's a number of technologies, but they fit different profiles, just like what you were talking about, which is how much power do you need and for how long of a duration do you need it? And so I'll talk a little bit about, that's pumped hydro storage there. And that's kind of the original bulk energy storage. And batteries have been growing in their capability, partly technology-wise, partly with price coming down, so that they're extending to larger and slightly longer durations. But flywheels, ultracapacitors aren't on here, but they're down in that thing. So as you go along this sort of diagonal axis, you're moving from really solving the squiggles in the sine wave to here, out here, potentially capturing solar energy from the summer and saving it to the winter. So batteries, there are actually 6 lithium-ion battery chemistries. And you hear a lot, well, the Chinese have all the lithium or stuff. I hear this on mainstream news. Lithium is produced in China. It's also produced in Australia. It's also produced in South America. And usually the more limiting factor is some of the alloys in there, cobalt in particular, right? Because a lot of it comes from basically the Congo and some other. So it's actually some of the alloys that are, more geopolitical issue related than the lithium itself. Electric vehicle applications, no surprise, are mostly concerned about power to weight, energy density, and then stationary storage for basically, they'll often site the battery plants sometimes next to a PV array or a wind turbine, sometimes at substations. So it's providing generation, but it's also providing generation strategically within the grid nodes. And for that, you're going to have a lot. You're going to need efficiency. Weight doesn't matter so much, but efficiency matters. A high number of cycles. These things will charge and discharge multiple times a day. Fire safety is an issue. Some of the chemistries are less prone to overheating. One of the chemistries will vent some oxygen. So you get hot, you vent an oxygen. That's a good fire starting combination. The battery manufacturers are working on some pretty sophisticated systems to try to improve safety for that situation and to limit the degradation of the battery. Batteries they're still expensive, and there's a real question about will you get as many life, and so managing kind of the charge-discharge cycle and the depth of the discharge is significant in managing the overall battery life. Most of the current plants are sized for 4 hours or less, sometimes a lot less, like that hybrid plant I showed you, maybe is 15 minutes. In California, 4 hours is what the CAISO uses for what they call resource adequacy. So you'll see plants often sized for that here. Some places they're less. There's different rules in the different power pools around the country, and so batteries have different rates of market penetration depending upon those rules. Texas in particular had some fairly strict rules for batteries. I hear that's changing a little bit, so they may get a little bit more battery storage there. There's obviously a lot of wind in West Texas. And then even in the battery sphere, besides lithium-ion, there's sodium sulfur. There are some other chemistries. And then for longer duration, people are talking about flow batteries. So it's basically it's a kind of a liquid that goes from, kind of a hot tank to a cold tank, if you will, reacting in between, cycling it back and forth. And so that's another thing. So this is just TEP, Tucson Electric Power. We're down there touring. They've got one of those engine power plants under construction. So we were there with a utility group last month. We didn't go see these battery plants, but again, here you can see this is essentially a 15-minute. If you basically divide the output and the capacity, so they're quiet. You can have them near your residential areas and things like that. So just to show you what some of them look like.
How quickly are they?
Pardon?
How quickly are we seeing those sprouting up?
Well, not as quickly as you're seeing photovoltaic, utility-owned photovoltaic things, usually in 10 megawatt bundles. Those are even more prevalent. But they are, I don't know, there was famous in Arizona, another company down there, Arizona Public Service, did have one catch on fire. And that was a kind of rippled through the industry. And they are ordering more of this. By the way, these are two different, remember I said there's 6 chemistries? So 2 different manufacturers, 2 different chemistries. So there's, maybe the electric vehicles are mostly in one particular chemistry. It's called NCA. I could figure out what nickel, cobalt, aluminum, I think, is what that stands for. There's about 3 or 4 of them used in stationary storage. So there are some differences between them in terms of number of cycles and other facets. But moving on. So energy storage. Most of the rest of these slides are all going to be about energy storage, grid scale energy storage. And so the original was pumped hydro, right? Here in California, they built Diablo Canyon in the nuclear power plant, PG&E, in the late 70s and early 80s. At the same time, up in the Sierra Nevada mountains, they basically had 2 hydro reservoirs that they basically connected and called Helms Pump Storage, right? So it's Wishon and Cartwright. Cartwright's a higher one, nice backpacking right out of there, actually. And so what the intent was there is because once nuclear plants, you just line them out. You don't want to move them up and down in load or change anything. And so if the nighttime load would dip into where the nuclear was, you got to send that power somewhere. So the idea was at night you would pump it up. Basically you have a motor generator, reversible motor generator. You would pump it up to the top reservoir at night. And then when you had the peak, and the day, at that point it was still in the afternoon, now it's in the evening, or whenever, or maybe it's a cloudy day when the sun's not out, you flow it back down, and it operates like a traditional hydroelectric power plant. And so in the modern, what are they doing now in the modern? So the problem with the good news about these is they're reliable, there's no emissions, there's not everywhere it's about a 2,000-foot elevation change between the 2 reservoirs for the PG&E Helms. Not every place has that. So You're limited in location. So some of these schemes you'll see in a minute are trying to get around, well, what if I'm in, Illinois or some other state that doesn't have that kind of elevation change? Yes, Peter.
Is Norway doing a lot of that sort of thing, or?
Norway has a high percentage of their power is just hydro itself. So if you had enough hydro, then you can modulate the hydro itself, right? You just throttle it. So they still have, I don't know what it is, but something like 70–80% or whatever of their power is hydro, right? So some of the Quebec in Canada and British Columbia also have a high percentage of hydro. So they may have some, I don't know, but they don't need it as much because to my knowledge, there's no nuclear. Sweden had nuclear. Norway didn't. So in the modern, what are they doing to modernize it? Basically, they're putting in variable speed drives now so that you can modulate it a little bit more. Again, to help, instead of it being more about just load shifting, about being flexible response to the grid, to the intermittency. The other thing is with the modern design, computational fluid design, just like with gas turbines, you're getting these very complex airfoil shapes. And so they've really bumped up the efficiency and versatility of pumped hydro in the few places you can put it in now. So what are people looking at instead? This is a little bit more of this is not built, this one here. This idea was, okay, well, it's going to be pumped hydro. We're going to have the same pump turbine reversible, but we're going to take tunnel boring equipment, and we're going to basically make a shaft, a well, basically a big well, 1,000 meters deep. And when we carve it, we're going to get basically this is basically a big rock piston from where they were drilling that thing out, and we're going to put doesn't have to be a super high tech, but some kind of sealing mechanism, and we're going to flow the water, basically just raise it up and down, and when we pump it up, when we need to take power from the grid, and we let gravity push it down when we want to deliver power to the grid. So, and they've, the company, it's a company here in California, and they've got, they've figured out where, what kind of rock formations, you're not going to drill this through granite. So it's got to be sort of soft enough but hard enough, if you will. And so sandstone and limestone are actually fairly prevalent geologic strata. So that's their concept.
What's the efficiency of these things?
This one would actually have, basically these pump turbines are fairly, I think you can get like 75, above 75% efficiency on these things. So it's probably, you're not going to have a lot of, this thing is moving slowly. There's not a lot of friction losses. So it would probably have pretty good
That would be higher than pump storage, right? It's about 70?
Yeah, it should be roughly comparable. I can't think of why this would be better than pump storage, so it's going to be, in the neighborhood. This is a proposed plant, but they've got their permits. I don't think they have the full money for this, but they've done a pilot, right? This is the the weighted, basically heavy rail cars on an electrified rail system, and you go up the hill when you're absorbing power from the grid, and you come down by gravity when you want to generate power. And this is how, they've got a site in Nevada with the track. It's got a pretty steep slope, so you don't need to give the cars a push. They'll go when you want them to go. And they were going to, basically respond to what the grid dispatch was. They were going to have, I think, 7 of these shuttles. And they could control the speed by which the number and the speed that are out there running, and that's how they would meet whatever the dispatchers wanted them to absorb or supply back. So again, you need the elevation difference, right? So this essentially, it's like pumped hydro where it's dry, and so you don't have the water, you're going to put in a train. There was one that was kind of, it's not viable, it's not going anymore, but it was basically like a ski lift. And they were going to have essentially like weights on the chairlift, and it was going to be the same kind of pump it up, let it fall back down sort of scenario. So people have come up with creative. This company here, Energy Vault, just got $110 million from the SoftBank of Japan. Now, they're the ones they got it before, I think, the Uber and WeWork, which are giving that SoftBank a little bit of a financial hit right now. But this company out of Switzerland, but it had California venture capital behind this, and it was going to be a 6-arm crane, and basically it's stacking, and it's got each of these blocks, 35 tons, it's, whatever, of concrete, and just a concrete block, and they actually found that they needed the full strength concrete at the top and the bottom where the blocks rest on one another. In the middle, they didn't need full strength concrete, and so they were going to mix in demolition waste, coal, basically stuff that people would pay to get rid of into their concrete block. So they had worked this out, and they had this system that was going to basically stack and unstack these things. These arms would move. Essentially, 4 would normally be in motion at a time. So you can see here, they're going for longer duration storage. Most of the schemes I'm showing you are people looking for longer duration than what can be provided by the battery.
So is this a Lego spin-off?
So, well, no, that's the first question. First question, and the guy had a good answer. He goes, like Jenga, not Lego. Meaning there's no interlocking, they just sit right on top of one another. And they actually had Caltech did a seismic study. This thing can withstand a 7.0 earthquake. And it's got vision, basically a vision control system. The real IP, the key to this is they can counteract wind loads and the pendulum, because you have to pick it up and move it laterally. So when you laterally move something on a crane and you want to stop, it tends to swing for a little bit, and you have to wait, and then you can set it down. That was going to screw up their system because they need to keep continuous motion. And so that's kind of one of their key IP is the basically overcoming the pendulum effect. And the same thing, they can vary the speed. They got variable speed drive motors on the winches to lift these things up and down. All right, let me go over a few more. So those are all gravity systems, right? The other thing, this has been around again, got a plant with 40 years, another plant with 30 years of experience, was in a flat area, Germany and Alabama. Well, Germany's got some mountains, but this is in the flats of Germany. Same with Alabama, where you have a geology called salt dome. Right? And so you can solution mine out the salt domes. That's been done for the actual salt itself. It's been done to create caverns. So it's like a real underground cavern. I think most people, when you talk about pools of oil and drilling for oil, they may imagine that it's something like a cave or whatever under there filled with oil, when in fact it's just basically like a rock sponge, a series of little pores that the oil is normally flowing through when you produce oil. But in the salt dome, and this type of geologic formation, you can basically get a whole cavern. And so it was a similar kind of thing. Compress air, stick it down in the dome when you want to absorb energy from the grid, run it out and expand it when you want to generate power. Now, as you all know, compressing air generates a lot of heat. Expanding air cools things off a lot. So what they did in these original designs is they'd basically, it would be a gas basically a modified gas turbine was their expander. And they would inject gas and, in a combustor and fire it up. They got a real good, kind of effective heat rate on that gas addition. And they avoided any kind of issues of freeze up or brittle, basically the metal not being, losing some ductility at very low temperatures. But there have been people who basically say, we are going to find out ways to capture the heat of compression, store it, and return it on the expansion cycle so that we don't have to use any fossil fuels, right? It's going to be a greener version of this. We're going to have higher efficiency because in the traditional case, the heat does basically dissipate out of the cavern just into the earth. And there have been a couple of sort of high-profile failures, not catastrophic failures, but financial failures of people trying. There's still a couple people out there that claim they have schemes to do this. It has not yet been proven. But this is another one. The only problem with this one, just like you need the elevation, here you need the salt dome geology. Now they've said you could do this in just basically a shale-sealed sandstone reservoir. That's an oil and gas formation. If it was so-called compartmentalized, meaning it didn't have a long lateral run. Not proven yet, but claimed to be done. So the problem here, again, though, is these things are pretty big. These caverns, you've got a lot of air. Well, somebody came along and said, how could we store that, give it a more compact footprint, and have it where I don't have one of those salt domes? Well, we're going to basically, turn the air cryogenic. Okay? So we're, liquid air, basically, oxygen, nitrogen, is a very, very compact way of storing it. And so this is the same kind of thing. You bring the air in, you compress it, you refrigerate it, and you basically you have two heat stores in this. You have basically a hot heat store and a cold heat store, and you cycle these things back and forth, and but it's similar to compression expansion, kind of like compressed air. I'm going to move, just to make sure you guys get out of here at time, I'm going to move a little bit quicker here through some of these. This is, so thermal energy storage, at large scale, has been proven, is molten salt. So this is a blend of nitrate salts. When you get it up to temperature, it basically has the viscosity of essentially like room temperature water. And so this is a power plant in Nevada with the power tower, the focus mirrors on the glowing white hot receiver. And for this particular thing, the salt is the heat transfer medium and the storage medium. So, and then you've got basically steam cycle generation down below. And so that's like a standard, high, basically power industry, high pressure, basically steam turbine inlet temperature. And so even their cold tank is still hot because you don't want it to solidify. You always keep it in liquid form. It works. Salt works. Salt's expensive, relatively expensive, but it's stable. You don't have to basically have a purge stream and a makeup stream. It's as long as you don't overheat it. It's very stable, and it has a low vapor pressure. So you can just use regular carbon steel tanks. They're not pressure vessel rated vessels because they're pretty big here in this particular case. So that's that. But people said, well, the salts, yes.
Question.
Yeah.
Is that the one you see when you fly over?
Well, there's Ivanpah is in the southern Mojave Desert. This one is it's kind of a little bit south of Reno. So I'm not sure where you're flying. Okay.
How are you getting energy out of this?
So, well, it's basic. You're basically doing a steam Rankine cycle. Okay, but people have said, well, that salt's expensive. Let's find a cheaper way, a cheaper material. Concrete. Well-established infrastructure for manufacturing concrete. And, okay, you don't have to haul it very far, right? That's a big expense. So you basically build a concrete plant next to your site, and you make these blocks you put in, you got tubes in there. So your water, steam, you can mate this up again with a Rankine cycle plant, flue gas, whatever, basically whatever your heat transfer fluid is. And you can stack these things up. And so this is actually being pilot scale, being built and demonstrated at like a 10 megawatt pilot scale right now. So, and other people have looked at crushed rock, sand, other low-cost things. Okay, how do you, again, now you want to make it more compact, right? They were trying to make it cheaper. What if you want to make it more compact? This company is out of South Australia. That's 1414 degrees centigrade, which is the melting point of silicon. So you're talking super hot, refractory line kind of storage vessels. So salt is pretty high in terms of, now they were keeping it all molten, but if you do use latent heat, there are some people that say, look, phase change energy, right? That'll make it more compact. And silicon has some of the highest latent heat of materials. And so they are cycling through basically from solid up into liquid range here. And they're targeting maybe more industrial and smaller scale utility applications. They're not trying to make a system as big as pumped hydro. But these guys are also doing a demonstration. South Australia, that's where Tesla was building the 100 megawatt battery plant. They've had, it's kind of grid isolated. They had some storm knocked out. It's kind of a poster child area for trying a lot of these sort of schemes. Malta is a company that was basically Google had Google X or Alphabet X sort of skunk works type lab, and they have just spun off something here called Malta. And again, this is where it's heat engine type stuff, right? So you can either heat with resistance, or you can heat by basically doing a heat engine. Then usually it's a kind of a air Brayton cycle on the output. Again, I'm not going to read you through all these, but the point is these guys got some of these people are getting significant money. These guys got Gates's Breakthrough Energy Ventures. I put money into this. So Flywheels. You asked about Flywheels. This can't claim. Flywheels basically. They're usually either steel at a fast but not super fast speed, or carbon fiber at a super fast speed, right? Because the energy storage is a function of the mass and the rotational speed. And they typically put them below grade. So if anything ever happens, it's bouncing around below grade. But there are a couple flywheel companies that have gone out of business, but there's one right now, Amber Kinetics, putting in stuff in Hawaii and Oahu. Hawaii is one of those places that has a lot of grid issues from high penetration of renewables. And there's a couple plants that are operating, even though their companies don't have money to build more plants. So one in Pennsylvania, I think the other one is in upstate New York, at 20 megawatt scale. So that's a big. The other place they're used is in electric rail transportation. They wanted to put one for many years underneath the middle of the bay for the BART system again, because the electric, there's a lot of regenerative energy, and you get a little voltage sag when you get far away. So Flywheels may take off more there, and I know in one of the companies I talked to is trying to get a deal going with it's either Boston or New York, basically one of their subway systems. Okay. This one you guys are going to like. Sun in a box. MIT. Okay. So liquid silicon again. So we're talking super hot. Again, they're just doing it by resistance heating. They're cold tank, 1900 C. These are all made of graphite. Everything's graphite. Pumps graphite. All this stuff's graphite. So what they do is they take the stuff, they run it through these tubes, and then they have tungsten foil. Well, tungsten, just like an incandescent bulb, it glows. And then they've got basically a PV cell. It's a multi-junction cell, so it pulls down into the infrared range as well as visible light. So it's a type of and so it's actually generating power by the glowing tungsten basically being picked up by, and then they raise the rod to modulate the output. They raise and lower the rod, changing the view factor. And it's actually, this is being built right now at a very, very small scale. I think like, 3 foot tall or whatever in a lab. But they can get super fast. I mean, as soon as you change the view, there's no inertia. As soon as you change that view factor, the output response is very instantaneous. And that's advantageous to dealing with those squiggles you saw earlier. This is just showing you this is not a US phenomena. Countries that are kind of the poster children for Germany. I don't see Denmark on. Germany and Denmark have some of the highest penetration of renewables. United States, it would be Hawaii. And then California, we're rushing headlong to try to catch up to them. Texas, Kansas, Oklahoma, there's a wind corridor there in the plains. So this is not. Lastly, then power to gas. You may have heard of power to gas. This was first pioneered in Germany, where they had excess renewables, and so they ran it through an electrolyzer to basically make the hydrogen. And then I don't have in this picture. They put the hydrogen into the natural gas pipeline. Okay, and you can have up to a certain percentage of hydrogen in the gas pipeline, no problem. Well, my first reaction is, well, you're taking basically hydrogen, a $10 fuel, you're mixing in a natural gas, a $3 fuel, what the heck? Find a use for the hydrogen. Right here in California, we use it for fuel cell electric vehicles. But it has the advantage of you don't have to spend any money on infrastructure, right? The gas infrastructure is there, not bad to start out with. It turns out these renewables guys had take or pay contracts, so they're going to, if they didn't take the power, they're going to pay for it anyway, so why not try this? So it's grown from there. And so now, again, though, you can generate it back, with a microturbine, various sorts of things to do grid. This is part of a study that for the Energy Commission, where it was this PUC had this thing called the Energy Storage Mandate. The IOUs had to buy a certain amount of capacity, and would hydrogen energy storage qualify? I'm going to wrap you up in just a couple minutes here. And so this is the original power to gas. Then my idea, well, put it in the vehicles, right? Don't put it, the law said you had to turn it back to electricity. Well, all right, you're turning it back to electricity at the drive wheel motor. How is that any different from plugging in your electric vehicle and charging it off the grid? So it turns out they didn't actually rule on that one way or another, but that was kind of the concept I was suggesting in this picture. The other thing you do is you got industries that use hydrogen, right? So why don't you site all these electrolyzers at an oil refinery, which has got a hydrogen plant there, and you can displace steam methane reform. Hydrogen is mostly made by ripping apart water molecule and methane molecule and recombining them. If the oil companies used a certain amount, they could get a credit. We have this thing in California called low carbon fuel standard. We're trying to reduce the carbon footprint of our transportation fuels. They get a credit for that. But when you start to go bigger up in scale, then this is a blended natural gas existing. That's a Germany example. But if you go really big, then people have said, well, what if you pull the hydrogen back out, right? Well, if it's more valuable, put it in a gas pipeline here, send it over there, and pull it back out in a different location. Well, you got to reseparate it, so that's an additional cost. Does it make sense or not? I don't know. I wasn't too optimistic about it. The other part of it is to make substitute natural gas. This is where that's being done right now a lot from biogas. That's another thing I'm not talking about here tonight, because this is mostly a grid talk. But certain states may be passing renewable portfolio standards for natural gas. There's a growing, they used to take biogas and just run it as medium BTU, clean it up a little bit, run as medium BTU gas in engines at the location. But now you pull the CO2 out and you upgrade it to regular natural gas BTU quality and put it in a pipeline, and you get credits. So if you can link it to a transportation end use, you can get these things called RIN credits from EPA, so that's going on. And then the ultimate is, the long term. We want to go from summer solar to winter and, huge amount of scale. You can basically build out your whole hydrogen network, dedicated hydrogen storage reservoirs like natural gas storage reservoirs, pipelines, et cetera. So this is the longest term possibility. So let me click back here and.
Isn't anybody worried about the leakage problem?
Well, the thing about hydrogen, it's a small molecule. It's a reactive molecule. So I'm not so much worried about it leaking to the surface, because if it does, it's going to go straight up anyway. It can't pool or something and blow up or something right now. So there's no concern there. It's a dollar concern, right? Yeah, you lose it. But supposedly the geologists say, once you build up the cushion layer, right? In natural gas storage reservoirs, you have this thing called the cushion gas layer, which kind of stays stable. And the stuff that moves in and out is kind of, so they said that would apply for hydrogen too. So anyway, so then coming to summing up, I tried to hit, see this power to gas I was talking about at the end, that's here, pump, storage, compressed air, batteries, flywheels. So I tried to cover a little bit of all these. There's electrochemical, there's reversible chemical reactions out there. There's more stuff. There's a lot of creativity going into trying to find solutions, and particularly about people trying to come up with the larger capacity, longer duration stuff where they don't have to compete with the batteries. So, any other questions? Yes?
I was wondering if there was anything, you knew whether there's anything done in low heat differential temperature stuff, because we often we have all these very low heat differentials that we have living around us. And can we get something out of that?
This is like, I'm giving you a kind of an indirect answer. So first of all, the direct answer is I don't know of much going on in that area. But what it reminds me of is you'll hear somebody say, there's more energy in the ocean, the waves, the whatever, the power of the earth umpteen times. Well, the problem is it doesn't have enough energy density, right? If you were to try to put in a turbine, tidal power in areas that have super high tides, you can get some energy. But the challenge there is just like that. There's lots of low-grade waste heat. The challenge is how do you bring it together to have something of a high,
I was thinking of Drake Landing, in Alberta, where they're storing enough energy in a borehole to power and to heat and get domestic hot water for the community. So they've become stable. So they have this solar, liquid solar on it, and that works. And that's actually
no. It's if you have. It's kind of a little bit like the real estate maxim: location, location, location. Right? If you've got an ability to have your user next to where you generate the heat, you're onto something. But if you have to move it, that's the problem.
Well, but in Alberta, you've got quite a
yeah, yeah. Any other questions? All right. Well, thanks. Hopefully, I gave you a little, appeal to your alter egos, give you something a little different than buildings. Next time, if you are ever interested, I can see if one of these building guys can come talk to you. They do quite a bit of work on the California Title 24. They're working on the next generation regs and other sorts of things. They got a lab up there, just like you guys have labs. So anyway, thank you again.